September the 27th, 1964, Roland Beaumont climbed into X-ray Romeo 219's cockpit at Boscombe Down, strapped himself in and fired up the two Bristol Siddeley Olympus engines that had a history of catastrophic failures. 14 major malfunctions between December 1962 and July 1964, turbine blades shattering, fires, and one explosion violent enough to completely destroy the Vulcan testbed aircraft. The final test bench failure had occurred just 2 months earlier. The engines installed in X-ray Romeo 219 were only partially cleared, derated to reduce the possibility of the Olympuses tearing themselves apart. Not only that, the undercarriage was a nightmare of complexity that refused to retract properly. In the days before, Beaumont had been asked whether he'd risk flying this aircraft. His answer was carefully measured. Given the mounting political pressure on the program, he'd accept the risk for one flight only. They could chance running the engines at full power for takeoff for the first 2 minutes. But after that, they'd need to throttle back or risk losing the aircraft. The program couldn't afford another delay. Beaumont took off. 15 minutes later, he brought X-ray Romeo 219 back down to Earth. The aircraft flew as predicted and everything seemed to work. Well, everything except the violent undercarriage vibration that briefly blurred his vision on landing, but that could be fixed. 24 test flights would follow over the next 6 months. On Flight 14, February the 22nd, 1965, Beaumont took X-ray Romeo 219 supersonic for the first time, on a single afterburner, even managing to outrun the lightning chase plane. 6 weeks later, cutting torches had reduced most of the TSR-2 fleet to nothing more than a pile of scrap metal. Hello, my name is Joe and welcome to Aviation Republic. This is a story I've been wanting to cover for a while. I've been umming and erring whether I should or shouldn't, considering that still, even to this day, emotions can run high whenever TSR-2 is mentioned. And strong emotions tend to produce strong theories about who ended it and why. In this series, I've mainly stayed away from various conspiracies floating around. Not because they make for bad stories, but because the truth is far more interesting. What the documents actually show is both complex and more human than any conspiracy could be. This is the story of Britain's perfect failure and an aircraft that became something larger than itself. And it's not a story that can be reasonably told in a single video, not even a long one like this one, without cutting corners that this aircraft doesn't deserve. The people who designed her, built her, and flew her deserve better than that too. And frankly, so do you. So I've broken this into 3 parts. This first part covers how Britain arrived at the need for TSR-2, the competition to build it, the forced marriage between rival companies, and the design challenges that began piling up before a single piece of metal was cut. Part 2 gets into the electronics, the primitive computers, weapons, the troubled engines, the first flight, and of course the political forces closing in around the program. And part 3 is the aftermath. Be sure to click the bell icon so you don't miss those episodes. So, what happened? Well, make yourself a cup of tea and get comfortable. The answer starts nearly a decade before her first flight, when Britain maintained the infrastructure of a superpower, but without the resources to sustain it. The strategic pivot. November 1956. In a secretly coordinated operation, Israeli forces invaded Sinai while British and French forces occupied Port Said in Egypt, attempting to seize back control of the Suez Canal after President Nasser nationalized it. The military operation succeeded, but the political operation collapsed. President Eisenhower was furious, threatening to withhold IMF support, a move that would potentially crash the pound sterling. Other countries joined in. Saudi Arabia imposed oil embargoes and the Soviet Union rattled its nuclear sabers. Within days, under the threat of crushing American economic pressure, Prime Minister Anthony Eden accepted a UN ceasefire and the British troops withdrew. Dennis Healey, then building his reputation as Labour's most formidable voice on defence, watched the crisis unfold. The Suez Affair, he would later write, was a demonstration of moral and intellectual bankruptcy in conception and a political, diplomatic and operational disgrace in execution. But beyond the immediate humiliation, Suez exposed a harsher reality. Britain had lost a political position in the Middle East it had taken 40 years to construct. Since World War I, Britain had drawn boundaries, established mandates in Palestine and Iraq, and built a network of bases and treaties to protect the route to India. That entire architecture, from the Ottoman collapse through to 1956, fell apart in a week. Without American support, Britain could no longer act as an independent power. The economic exhaustion was profound. Liquidating foreign assets and spending sterling balances to finance World War II had left Britain facing appalling difficulties, simply paying for necessary imports. The balance of payments was a recurring crisis. Sterling remained fragile. Defence spending consumed resources desperately needed elsewhere. Yet when Harold Macmillan took office in January 1957, he chose to maintain Britain's nuclear deterrent, keeping sterling as a reserve currency and sustain extensive overseas military forces. The gap between ambition and resources would have to be managed somehow. However, the RAF's existing capabilities couldn't bridge that gap. The Canberra, first flown in 1949, in service since 1951, brilliant for its time, relied on speed, altitude and maneuverability to evade interception. This concept worked when it was conceived because Soviet defences couldn't reach it. By the mid-1950s, that advantage was disappearing. Soviet surface-to-air missiles were proliferating across the Middle East, Eastern Europe and Central Asia. The American U-2 spy plane would be shot down by an SA-2 Guardline missile in May 1960, proving that high-altitude flight had become what one RAF assessment called sheer madness. The V-bomber force, the Valiant, Vulcan and Victor all faced the same vulnerability. When the RAF attempted to shift them to low-level operations to compensate, fatigue life was cut catastrophically. A Vulcan's airframe life dropped from around 3,000 hours at high altitude to just around 300 hours when flown hard at low level, and technologically, the deterrent force was aging rapidly with nowhere safe to operate. The strategic nuclear deterrent, RAF Bomber Command's reasons for existence, was on borrowed time. The future seemed to belong to high-speed, low-level penetration aircraft, using terrain to mask approach, staying under radar coverage, maybe arriving too fast for defences to react. Suez wasn't just a humiliation, it was a technical lesson the RAF couldn't ignore. The Canberra squadrons deployed to Cyprus in October 1956 had operated from proper air bases with prepared runways, maintenance facilities and logistics support. They'd flown high-altitude bomber missions in clear Mediterranean weather against targets the Egyptians couldn't defend. That kind of war was over. Britain's global commitments demanded operations in places where proper air bases didn't exist. The Baghdad Pact covered Iraq, Iran, Pakistan and Turkey. The Southeast Asia Treaty Organization, or C2, extended obligations to Thailand, the Philippines and Pakistan. NATO required tactical strike capability in Germany. Limited wars could erupt anywhere along this vast arc. And Britain's small professional forces needed aircraft that could operate from rough forward strips, penetrate defended airspace and deliver weapons accurately without ground navigation aids. The Canberra couldn't do it. Too slow at low level, too vulnerable without defensive systems, too dependent on proper runways and ground support. The V-Force couldn't do it either. These were strategic bombers designed for nuclear deterrent missions from established bases. The Vulcan and her sisters were the wrong aircraft entirely for tactical strike. Britain needed something the Americans were already building in the F-105 Thunderchief. An aircraft that could fly low and fast using terrain-following radar and automated navigation systems to survive in defended airspace, plus the ability to operate from rough forward airfields. This was the operational problem the RAF faced in late 1956, when the first formal paper proposing a Canberra replacement circulated within the Air Ministry. Not a theoretical exercise, but an urgent requirement driven by the harsh lessons from Egypt and the changing nature of air defence. By March 1957, General Operational Requirement 339 was formally drafted, and it was this specification that demanded capabilities that had never been combined into a single airframe. But there was a problem. Britain was broke. The economic vice. Duncan Sandys had a solution to Britain's defence spending crisis. Appointed Minister of Defence in early 1957, Sandys was tasked with a total reappraisal of military capabilities. His mandate? Emphasise nuclear deterrence and missiles over manned aircraft, reduce expenditure toward a cap of £2 billion by the late 1960s. His April 4, 1957 Defence White Paper made the vision explicit. The era of the fighter pilot was ending. Interceptors would be replaced by surface-to-air missiles. Bombers would eventually give way to ballistic rockets, and Britain's sprawling aircraft industry, with too many companies chasing too few contracts, needed consolidation. Smaller and weaker firms would be forced to merge, with any new contracts going only to the best combined entities. The shockwave through the industry was immediate. Numerous projects died. The Avro 730 supersonic bomber? Cancelled. The F-155 interceptor? Cancelled. The SR-177 rocket plus jet fighter? Cancelled. Entire squadrons disbanded. Derek Wood, chronicling the period's upheaval, noted that more than 30 weapon systems were cancelled over a short period of years. The industry faced what Stanley Hooker, then at Bristol Aero Engines, called a time of great turmoil rarely equalled in any industry. The numbers told the story. In 1956, Britain had 22 airframe companies, 6 engine groups, and 4 helicopter manufacturers. The ministry's assessment was blunt. The industry was excessively fragmented, with too many design offices duplicating effort and consuming limited resources. Small firms like Blackburn, Fairey and Sanders Rowe lacked the resources for modern supersonic projects, and therefore they'd better merge or disappear. The RAF naturally pushed back hard. Senior officers argued that tactical mobility still mattered, that missiles couldn't provide flexible response to varied threats, that Soviet bombers would arrive before missile defences were fully deployed. Sandys relented slightly, allowing the English Electric P1, which would become the Lightning, to continue development. And quietly, one other project survived, a requirement for a camber replacement that had been formally percolating through the system since late 1956. The industrial landscape. On September 16, 1957, an extraordinary meeting took place at the Shell Mex House in London. Sir Cyril Musgrave, Permanent Secretary at the Ministry of Supply, faced the assembled heads of Britain's aircraft industry. Lord Caldecott from English Electric, Sir George Edwards from Vickers Armstrong, Sir Roy Dobson from Hawker Siddeley, Sir Frederick Handley Page, along with representatives from Blackburn, Bristol, de Havilland, Sanders Rowe and Shaw Brothers. Sir Cyril delivered the message with ministerial authority. Following the Defence White Paper, there was no certainty of future military projects except possibly GOR 339. The ministry would only place the contract with a group of firms or with 2 or 3 in coordination, one acting as leader. And proposals had to indicate which firms each company would associate with. The message to the collective heads of Britain's aircraft industry was unmistakable. For any hope of winning any major aircraft contracts, there would be work for free, perhaps at most 4 grouped units. Eventual amalgamation and rationalisation were the government's hopes. The RAF Historical Society paper on TSR-2 would later write that Sir Cyril Musgrave, speaking for the Ministry of Supply, emphasised the need for consolidation and stated that the only power the department possessed was in the placing of the contract, and it was intended to use this as a means of encouraging the association of firms. The requirements for an ideal association were laid down. Diversified military and civil programs, good design capacity including supersonic experience, and financial strength. The reaction from the industry was immediate. Questions about design responsibility, future projects, how partnerships would function. But the underlying reality was clear. The fragmented industry would be forced into consolidation. The government was using GOR 339 as what Sir George Edwards would later call Golden World in Flux. So it was either merge or get nothing. Stanley Hooker, who'd lived through the subsequent consolidation as Bristol Aero Engines merged with Armstrong Siddeley Motors to form Bristol Siddeley Engines, summed up the human dimension. People in the great pioneering companies of this British industry were passionately proud and loyal to their great names, and powerful emotions had to be eroded if mergers were to succeed. Few could doubt, Hooker wrote, that in the 1950s Britain had too many aircraft companies and too many military aircraft development programs. It was inevitable that both should sharply diminish. But perhaps this should have been possible without either suggesting that military aircraft were obsolete or that companies failing to merge should no longer be considered for government contracts. 7 days after the Shell-Mex House meeting on September 23, 1957, GOR 339 was formally issued to industry. The deadline for submissions, January 31, 1958. 9 companies would respond. What came back would reveal just how fragmented the British aircraft industry had become and how impossible it would be to satisfy the requirement without forcing competitors into uncomfortable marriages. 339. The Impossible Requirement. The first formal paper proposing an air staff requirement for a camber replacement had circulated within the Air Ministry in November 1956. By March 1957, GOR 339 was formally drafted. The specification laid out the requirements for an aircraft to have tactical nuclear strike capability, along with conventional weapons delivery, photo reconnaissance at multiple altitudes, and electronic intelligence gathering. Any submission would also have to operate in any weather without ground navigation aids, be capable of Mach 2 or better at altitude combined with high subsonic speed at sea level, plus have a combat radius of 1,000 nautical miles. And to top off the exacting demands, have a short field takeoff run from forward airstrips needing no more than 3,000 feet of runway. Author Andrew Brooks, in his technical analysis of TSR-2, wrote that the air staff had originally expected the project would be allocated a designation similar to that given to the V bombers. But TSR-2 was the designation by which it became universally known, the TSR denoting its roles, tactical, strike and reconnaissance. The rationale behind these requirements was really down to genuine operational uncertainty. Would the next war be total nuclear exchange with the Soviet Union? Limited conflicts east of Suez needing tactical support? Deterrent missions under NATO command? The specification tried to answer all of the above. Low-level penetration was essential because Soviet SAMs were making high-altitude operations increasingly dangerous, which led to the requirement for penetration at Mach 0.95 at a mean height of about 1,000 feet. Supersonic speed at altitude was necessary because interceptors were getting faster. Short field performance was required because NATO war plans assumed nuclear strikes would crater most proper runways in the opening hours of conflict. The navigation system had to provide accuracy within 0.3% of distance from the last fix. But perhaps the most critical requirement was buried in the operational notes. No single failure should prevent the crew from bringing the aircraft safely back to base. Every system needed redundancy, every component needed backup. GOR 339 progressed through multiple drafts. Throughout the process, the demands became more severe. The low-level penetration height dropped from around 1,000 feet to not more than 200. The aircraft needed to operate from rougher, less prepared airfields, meaning it had to be light enough to land on quickly prepared forward strips that couldn't handle heavier bombers. Meanwhile, at altitude speed requirements increased to Mach 2.25. GOR 339 was without a doubt ambitious. The technology existed in one form or another or was under development: terrain following radar, inertial navigation systems, high thrust engines with reheat, advanced avionics integration. But pulling it all together in one airframe would push British engineering to its limits. And the engineers didn't know it yet, but GOR 339 wasn't just a specification for an aircraft. It was a test whether the firms that had competed for decades could somehow still deliver state-of-the-art technology while being dismantled and reconstructed by political force. The trap. The political timeline was unforgiving. The 1957 Defense White Paper had declared manned aircraft obsolete, but GOR 339 had survived on a technicality. It bridged tactical strike and strategic deterrent, filling a gap missiles couldn't cover. But that meant the project carried permanent insecurity from day one. It would have to prove itself to politicians who didn't believe in it. The challenges extended beyond engineering. The period in office for ministers concerned with aircraft programs averaged roughly 1/12 of a typical project's timescale, yet each minister felt compelled to leave their mark even with negligible aircraft industry experience. Procurement policy shifted with every ministerial appointment, creating conditions where long-term planning became impossible. And, unlike every previous project, there were now 3 separate ministries involved: Supply, Aviation and Treasury. 3 bureaucracies, each with veto power, with no single authority responsible for success. Britain was trying to design its way out of geopolitical decline, and the question was whether the industry could survive the process. The engineers across Britain's aircraft companies had no illusions what was coming. This wasn't just aircraft development, this was industrial surgery performed under political anesthesia, and they had 4 months to make their case for survival. I want to take a second here to thank you so much for watching. I'm truly grateful to share my love of aviation with fellow enthusiasts like you. So if you're enjoying this story, please take a quick second to hit the like button. It's a small gesture that makes a huge difference in helping me reach more aviation fans. Now let's get back to the story. January 31st, 1958. 9 brochures arrived at the Ministry of Supply's offices in London. English Electric submission alone ran to 3 volumes with hundreds of pages, filled with wind tunnel data, structural calculations and exhaustive schematics. Vickers countered with nearly 300 pages of technical specifications and drawings. Avro brought powered bombs and standoff weapons. Bristol proposed a canard delta design. Fairey offered another canard layout. De Havilland submitted structural calculations that didn't quite add up. Blackburn pushed the NA-39 it was already building for the Navy. Shorts proposed a very ambitious vertical takeoff platform powered by no less than 70 engines. Hawker Siddeley made not 1 but 2 late submissions. The assessment group, led by Handel Davis, Director General of Scientific Research Air, with input from the Royal Aircraft Establishment and aerodynamicists, had never seen anything like it. Most requirements drew 5 responses at most, some drew only 1. GOR 339 had pulled in every major aircraft company in Britain, each desperate to win what might be the last significant military contract for years. Which was no surprise since the government had been clear at the September meeting: merge or get nothing. Now the companies were discovering what that actually meant. The contract wouldn't go to the best design, it would go to whoever could prove they'd consolidate the industry while delivering a viable aircraft. Technical merit mattered, but survival mattered more. The frontrunners: English Electric. The company with supersonic experience, wind tunnel facilities and test pilots who knew how to fly fast, arrived with confidence and 3 thick volumes. Volume 1 outlined the P-17A, the baseline design drawing heavily from the Lightning. But rather than the stacked Avons of their Mark II Interceptor, this aircraft would have a pair of engines sat side by side under a delta wing and a 600 nautical mile radius. Volume 2 covered the VTOL variants to satisfy the ministry's obsession with dispersed operations. English Electric had explored the problem systematically. Could you build a smaller, cheaper aircraft? Well, not without sacrificing everything the specification demanded. A single engine design was unsafe for supersonic operations. Shrinking the airframe was impossible. The cockpit, the bomb bay and engines couldn't be reduced in size. Even dropping to 60,000 pounds required using a less powerful engine which killed both range and takeoff performance. The P-17B emerged as a compromise. Dimensionally similar to the P-17A but using less powerful RB-133R engines that were supplemented by 3 RB-108 lift jets positioned forward of the centre of gravity. The lift jets were there to compensate for the weaker main engines during takeoff, and were expected to cut the takeoff roll by 25%. But the trade-off was brutal. 15% reduction in range, which pushed the already marginal combat radius further from the specification's demands. Empty weight of 39,000 pounds and a maximum weight of 72,000 pounds. But English Electric wasn't proposing this as a serious solution. The P-17B showed that trying to save time and cost by using existing engines while patching performance gaps with lift engines simply didn't work. You ended up with an aircraft that was neither cheaper nor better, just differently compromised. Then there was the P-17C, which went further still. 28 RB108 lift engines crammed into an enlarged airframe for full vertical capability. The weight became crippling. At 112,900 pounds of maximum, vertical takeoff was only possible up to 83,000 pounds, barely enough for short-range missions. And the 1,000-mile sortie, impossible without a conventional runway takeoff. It was obvious that a VTOL aircraft using internal lift engines trying to meet everything GOR 339 demanded was always going to be compromised. But there was a possible solution. Volume 3 was the alternative from Short Brothers, and with it, the formal partnership that bound the two companies together. English Electric and Shorts had signed a written agreement in February 1958 which stipulated equal work share if either firm won the contract. Short's contribution, drawing directly from the SC-1 VTOL research experience, was the P-17D lifting platform. The concept was technically ingenious and operationally mad in equal measure. The platform was a 77-foot crop delta flying wing powered by 56 RB108 engines split into 3 groups, 36 fixed engines exhausting straight down, 12 tilting engines, and 8 propulsive engines for forward thrust. The general idea was that the English Electric P-17A would sit on the platform, which would then lift off vertically using those 36 lift jets, followed by transition into forward flight and accelerate to 250 knots, at which point the P-17A would be released to fly its mission. Recovery was even more ambitious. The P-17A would rendezvous with the platform in mid-air, match speeds and use infrared sensors to lock onto the aircraft to guide it back onto the deck. On paper, the operational possibilities were interesting. The platform could double as a tactical freighter or as an aerial tanker. Shorts argued that every cargo ship with sufficient deck space could become an aircraft carrier. Pre-positioned platforms could enable surprise attacks from unexpected ranges, with P-17As refueling and rearming before striking targets deep in enemy territory. But the engineering challenges, however, were sobering. The exhaust from 56 jet engines operating simultaneously would be severe. Even English Electric's own illustrations showed ground crews wisely retreating to a safe distance. The specification estimated that the platform would weigh 46,000 pounds empty, nearly as much as the aircraft it carried, and needed an additional year of development beyond the P-17A just to achieve basic flight testing. The mid-air docking procedure required perfect weather functioning systems on both aircraft and crews willing to attempt something that had never been done even experimentally. Loading and unloading required winches or cranes, yet another layer of operational complexity that made the concept impractical. English Electric acknowledged all of this freely in their submission. They admitted 56 engines was an unattractive concept and suggested various combinations of more powerful engines to reduce the count, though any practical system would still need enough redundancy that losing several engines wouldn't mean losing control. By showing that liftjet variants destroyed performance and lifting platforms required extraordinary operational complexity, English Electric made their conventional P-17A appear as the only rational choice. What English Electric didn't say in the brochure was that their partnership with Short Brothers, formalized in that February agreement, was about to become another casualty of the consolidation process. The assessment group's evaluation of English Electric revealed a telling contradiction. The company had what assessors called excellent team spirit, with consistent strong technical ability from senior staff all the way down to junior engineers. However, that confidence did not extend to top-level management, which it found was exceedingly tenuous. The company also declined to provide firm cost estimates, stating that it wasn't public policy to quote prices without a solid specification. English Electric eventually produced a paper called The Economics of GOR 339, still refusing hard numbers, instead lecturing the ministry on crude estimation methods and warning that miniaturization could increase costs despite saving weight. But the ministry needed numbers, and English Electric's refusal looked like arrogance. On the other hand, Vickers emphasized miniaturization, pushing for compact modules that would reduce equipment volume from 300 cubic feet to just 80. Sir George Edwards' reputation, delivering the Valiant on time and on budget, gave the approach credibility. Their brochure included cost projections, schedules, and clear illustrations. There was even a section on export potential. But engineers at a Royal Aircraft establishment, even though approving of the idea of miniaturization, found insufficient depth in the claim that Vickers put forward about their module packaging. For instance, they had omitted explaining thermal management. Where would cooling air circulate in such dense modules? Interest and skepticism in equal measure. Within the Hawker-Siddeley group, Avro put forward the Type 739, one of the several competing answers to GOR 339 generated inside the same conglomerate. It was in isolation a credible submission. Avro's brochure included thorough aerodynamic calculations, one of only a handful of proposals to do so. That was no surprise. Avro had deep experience with large delta-wing aircraft from the Vulcan program and understood the structural realities of sustained high-speed flight. The Type 739 also introduced powered bombs. These were standoff weapons intended to keep delivery aircraft miles from heavily defended targets while carrying larger warheads. But credibility ended at delivery. Roy Dobson's schedule claims 3 prototypes in under 3 years rang hollow when he argued that sheer willpower would overcome development risk. The ministry wasn't persuaded. The Type 739 failed not because it was incompetent, but because it was one proposal too many from a group that couldn't decide what it was trying to build. That confusion defined Hawker-Siddeley's response to GOR 339. So rather than presenting a unified weapon system concept, the group submitted multiple internally competing designs. Avro had its 739, Gloucester offered another proposal, Hawker put forward an enlarged derivative of the P-1121 supersonic fighter, an aircraft Hawker had continued developing with private funds after the 1957 white paper killed the interceptor requirement it was designed for. When the ministry made clear in June 1958 that consolidation was mandatory, Hawker-Siddeley management attempted to impose unity after the fact. A single resubmission was demanded from the group as a whole. Sidney Cam, designer of the Hurricane and Hunter, now 64 years old, was placed in charge under the oversight of Avro's technical director Stuart Davis. The assessment group found the arrangement deeply concerning. Cam and Davis brought forceful personalities and incompatible design philosophies to what was supposed to be a unified effort. The resultant aircraft proposals mixed the modified P-1121 with the P-1129, which incorporated selective Avro features. Cam was in effect trying to rescue the P-1121, nearly complete with major assemblies built and wind tunnel testing finished, and it was sitting in the Kingston experimental shop. He attempted to adapt it for both interceptor and strike reconnaissance roles, but the assessment group saw organizational chaos, not visionary multi-role thinking. The assessment was blunt. Hawker-Siddeley had muddied the waters with its various submissions, raising serious doubts about whether the group could deliver a coherent weapon system at all. Ultimately, the assessment group would have to decide whether a capable design from a dysfunctional organisation was better than the alternatives. So for now, the P1121 sat nearly complete and increasingly irrelevant to a competition that almost seemed like it wasn't really about aircraft at all. Hawker Siddeley was the future the ministry claimed to want, a consolidated group capable of aircraft development. GOR 339 would soon reveal how poorly that future actually worked. The also-rans. Bristol's Type 204 Canard Delta looked promising until the Royal Aircraft Establishment examined the stability calculations. The design sat uncomfortably close to the configurations the RAE had tested for future supersonic transport, configurations that had proven problematic. Worse, Bristol's drag calculations contained fundamental errors. That submission died within days. Fairey's Canard design faced an altogether different problem. The foreplane created interference with the intake system and lateral stability looked questionable. The design might need twin fins to compensate, but none of this mattered. Fairey's aircraft couldn't achieve realistic supersonic performance at low level. Brief examination, swift rejection. De Havilland's structural weight claims looked optimistic when checked against required fatigue strength. The numbers simply didn't reconcile. Blackburn's NA-39, already being built for the Royal Navy, couldn't meet the supersonic requirement and was dismissed within days. Of the 9 companies which had responded, just 3 emerged as serious contenders: English Electric, Vickers and Avro. The rest were eliminated. Insufficient facilities, inadequate teams, unrealistic proposals. But even among the 3 front-runners, no clear winner existed. The assessment group was looking for an impossible choice. What 339 seemed to be really testing wasn't design brilliance, but institutional obedience. The ministry needed an aircraft that could survive Treasury scrutiny, force consolidation, and be managed within a shrinking defence economy. Technical excellence mattered, but only insofar as it didn't threaten control. In that sense, the competition was already rigged against any firm that behaved like an independent designer rather than a compliant systems integrator. The assessment group's task wasn't to choose the best aircraft, but the least dangerous winner. And meanwhile, a much bigger fight was brewing. The RAF's first strike. In April 1957, months before GOR 339 was even formally issued, the Ministry of Defence sent a letter to Sir Claude Pelly, the controller within the Ministry of Supply, that exposed just how ruthless inter-service warfare could get. The letter proposed cancelling Blackburn's NA-39 to save money. The Royal Navy could make do with a developed scimitar instead, cheaper and already in production. The letter helpfully pointed out that killing the NA-39 would enable the government to eliminate both Blackburn Aircraft and de Havilland Engine Company earlier than planned as part of the industry rationalisation. But the real goal was buried deeper. The plan was to demonstrate that the RAF GOR 339 aircraft could eventually cover all Royal Navy strike commitments, enabling removal of the entire naval carrier fleet. 2 problems solved with 1 cancellation. However, the ploy failed. In August 1957, the NA-39 program, what would become the Buccaneer, was allowed to continue. The RAF's case was blunt. Blackburn's aircraft was subsonic at low level, lacked supersonic dash capability, and couldn't meet GOR's 339 range requirements. Whatever its merits for Royal Navy's maritime role, it wasn't the sophisticated high-speed penetration aircraft the operational requirement demanded. But the damage was done. Admiral Louis Mountbatten, first Sea Lord, became what the ministry later described as an implacable enemy of GOR 339. He believed the future of Britain's nuclear deterrent belonged to the Royal Navy, not aircraft, and not to the RAF, a conviction that would prove prophetic. Mountbatten's signature tactic became legendary in Whitehall. The Sunday Times reported that Mountbatten would arrive at meetings and slap down 5 photographs of the Buccaneer next to a single TSR-2 image, declaring 5 of one or 1 of the other at the same cost. The Royal Navy's aircraft could deliver equivalent capability at a fraction of the cost, he argued. The opposition even extended beyond the walls of Whitehall. When Sir George Edwards toured Southeast Asia promoting TSR-2 to Australia, Mountbatten followed. He informed Australian officials he doubted whether TSR-2 would ever enter service, primarily on the grounds of cost and complexity. The intervention proved devastating. By March 1964, the Australian Air Minister publicly stated his doubts the RAF would order 100 TSR-2s, noting the uncertainty would continue if the present head of the UK Chiefs of Staff remains in authority. This wasn't unprovoked aggression, it was retaliation. The RAF had tried to kill the Buccaneer and possibly Naval Aviation to clear the field for GOR 339. Instead, they had created an opponent who would undermine the program at every opportunity. The assessment. The assessment group led by Handel Davis and the Air Ministry representatives began work knowing the responses would take months to evaluate properly. Facilities varied significantly. English Electric at Warton and Avro at Woodford had adequate runways for testing. Vickers runway at Wisley in Surrey was a little shorter than the emergency safety minimum laid out by the specifications. Although every firm had sufficient manpower, indeed most were overmanned, reinforcing one of the consolidation's key purposes, reducing capacity, not increasing it. On advanced systems such as terrain-following radar and automated navigation, the submissions provided scant details. These were, to be fair, bleeding-edge technologies that barely existed in prototype form, and those that did were still in the very early stages of development. But there existed no fully integrated operational system in 1958. Scientists from the Royal Radar Establishment believed terrain-following radar was unlikely to be ready in time for the proposed service date. The technology was theoretically sound, but immature and would need to be integrated later once proven. Vickers' miniaturization concept generated intense discussion. If the approach worked as claimed, the aircraft might be small enough to appeal to export customers, lowering unit costs through volume production and making the program economically survivable. But the evidence supporting the claims remained thin. The data they had provided couldn't verify thermal management in such densely packed bays. Avro's powered bomb approach, these standoff weapons, would keep the delivery aircraft miles from heavily defended targets, which meant safer delivery and larger warheads. The concept had merit, though it added complexity and cost. Speaking of costs, these estimates varied wildly. English Electric refused to provide firm numbers without a fixed specification. Vickers projected development costs around £90 million, with unit costs of £2 million per aircraft. The ministry's internal target was considerably lower. Nobody knew if any of the figures were realistic. By March 28, 1958, after months of analysis, the assessment group reached its recommendation. English Electric should lead, partnered with Vickers and Shorts. The companies were duly informed that their work was first class and 339 was essentially theirs. This arrangement lasted all of 4 months. On July 8, 1958, Controller of Aircraft Sir Claude Pelly reversed course. English Electric's technical abilities, already praised in the March assessment, were reaffirmed, but management confidence remained exceedingly tenuous. Sir George Edwards at Vickers, by contrast, inspired complete confidence. Technically strong despite aerodynamic gaps, precisely where English Electric excelled. The logic was clear. Vickers leads, English Electric supports, Shorts eliminated. On July 14th, the R&D board agreed. Shorts' name was conspicuously absent. Then came the fatal meeting. On July 29, 1958, Chalmers House, London, Minister of Supply Aubrey Jones met with representatives from both companies, Lord Caldecott from English Electric, Sir George Edwards from Vickers and their respective teams. What happened next would poison the partnership before it even began, a complete dog's breakfast. Jones, attempting to explain the government's thinking, made a catastrophic statement in front of both companies. We preferred the English Electric design, but we also preferred the Vickers management. The reaction was immediate. Vickers left the meeting convinced it would be in charge of the entire project. English Electric left believing the P-17A was the aircraft to be built and Vickers was merely providing management support. Sir Claude Pelly tried to explain that GOR 339 wasn't about choosing a design but about investigating feasibility, but it was far too late. Jones had said the quiet part out loud and the resentment was baked in. Handel Davis, who'd led the assessment group, would later admit with considerable unease that the decision had been made to exploit Edwards's management capabilities. Davis noted that this was faithful to the government's line of using TSR-2 contract to force amalgamation on the industry. But he acknowledged that the outcome had troubled him. Edwards's attention would be divided by the VC-10, Vanguard and other civil projects, preventing the focused leadership the program needed. Throughout the project to come, English Electric would believe Vickers had stolen its aircraft, and Vickers would believe it had rightfully earned leadership through superior management. And negotiations to form a joint company would suffer from Vickers' attitude that it was the boss in any partnership. The casualties. Shorts fared even worse. The company had a written agreement with English Electric from their joint February 1958 submission, equal work share if either won. The government ignored it by reissuing the requirement as OR 343, claiming the original agreement no longer applied. Shorts was excluded from a design its engineers had helped create. The company had partnered with English Electric on the P-17D lifting platform concept and they wanted their agreement honoured. The ministry's position was unequivocal. This is OR 343 and not GOR 339. A bureaucratic sleight of hand, some might say. And to add insult to injury, when Shorts claimed design rights on the RB-108 lift engines from their joint submission, the Ministry of Supply dismissed it as preposterous. The SC-1 research aircraft and the RB-108 engines had been entirely funded by the Ministry. Therefore, anything derived from this work belonged to the Ministry to exploit for defence purposes as they wished. English Electric attempted to salvage the relationship. In June 1959, they wrote asking for assurance that any future English Electric Shorts partnership would be accepted on its own terms. The Ministry replied, apologising that they felt unable to give such assurances, so the message was unmistakable. Although the Ministry couldn't force partnerships legally, partnerships existed only as the Ministry permitted, on the understanding that they would refuse to award contracts unless companies did as they were told. Every other firm in Britain watched and understood. The impossible marriage. On January 1, 1959, the announcement was made public. The contract for the aircraft that would become TSR-2 would be undertaken jointly by Vickers Armstrong and English Electric. The work would be shared on a 50-50 basis. A joint project team would be established at Vickers Works at Weybridge, but all subsequent contracts would be placed with Vickers alone. English Electric would be treated as a subcontractor. Design leadership, project management, specialist activities, all controlled by Vickers personnel. The only exception was the flight test, where English Electric would lead because Vickers had no one with substantial supersonic experience. The engineers at Warton and Weybridge now had 12 months to produce a joint design before metal needed cutting, a 1975 solution using 1960s tools constrained by 1950s politics in service of a 1945 strategic mindset. January 1959. George Henson sat in a Vickers Weybridge design office surrounded by engineers from two companies that had just spent months trying to prove the other was wrong. Henson, ex-Supermarine, now leading Vickers' joint project team, had 12 months to merge English Electric's P-17 with Vickers Type 571 into a single aircraft. His second-in-command, Ivan Yates from Warton, brought English Electric's supersonic experience, and together they were supposed to create what one historian later called a sensible and practical compromise. But neither company believed compromise was possible. English Electric's team at Wharton believed the P-17 with their delta wing, their aerodynamics and their lightning experience had won on technical merit. Vickers, on the other hand, believed Sir George Edwards's management authority and miniaturization concepts gave them leadership. The ministry had managed to tell both companies exactly what they wanted to hear and neither what they needed. From the beginning, emotions ran hot. At English Electric, Vickers were seen as arrogant interlopers trying to take over the Canberra replacement. At Vickers, English Electric were dismissed as cheeky young upstarts with nothing but the Canberra and as yet unproven P1 under their belts. Vickers believed their Valiant and Scimitar experience put them in an unassailable position. After all, they delivered Britain's first operational V-bomber on time and on budget. English Electric, still wet behind the ears, had some nerve trying to go it alone. The ministry forced them to collaborate anyway. But here's what really made the TSR-2 different from every aircraft that came before it. The complexity wasn't imposed by physics or engineering, it was manufactured by institutions. Every technical challenge had a committee attached. Every design decision required approval from companies that fundamentally distrusted each other's methods. Nobody had the authority to impose trade-offs, nobody could say no. Henson understood aerodynamics and structures, what he couldn't control was the system built around him. The committee machine. Author Derek Wood, who studied the program's management extensively, documented what happened when committees replaced chief designers. On previous aircraft, designers like Sidney Cam at Hawker would have made firm decisions within half an hour and stuck to them. The Hunter, the Sea Fury, the designs that had built British aviation's reputation, these emerged from individual authority backed by experience. One person decided, everyone else followed. The TSR-2 was different. Committees examined every aspect of the project and disagreed on most of them. No single person could or did take instant decisions based on experience. The management board referred decisions to the systems integration panel. The panel consulted the subsystems committees. The committees formed working parties. The working parties reported back. Recommendations were considered and new meetings were scheduled. Derek Wood noted that designers of Cam's generation would have been horrified. They understood that aircraft design required trade-offs and trade-offs required authority. Someone had to decide that this requirement mattered more than that one, and someone had to accept that you couldn't have everything. On TSR-2, nobody had that authority. It became commonplace for 60 people to sit in on ministry meetings discussing technical problems for hours without resolution. At one session, the chairman counted 58 attendees. He complained that the number was unmanageable and demanded a reduction. And the next meeting had 61 people. The escalation was structural, not accidental. Each company wanted its interests represented, each ministry department wanted oversight, each technical specialism wanted input. The committees that could stop progress multiplied faster than the engineers who could create the aircraft. The philosophical clash. The design team at Weybridge of roughly 40 people were working with drawings from two different companies and no common design in being. Naturally, the disagreements and arguments started immediately and never really stopped. English Electric had provided 225 cubic feet of equipment space in the P-17. They'd learnt from the cramped installations on the P-1, insufficient room for systems meant maintenance nightmares and operational limitations. Give the equipment room to breathe. Vickers called this empty air wasteful. Their design allocated roughly 90 cubic feet. Equipment bays that would be practically empty, they argued, represented wasted volume that could carry fuel or reduce airframe size. English Electric countered that Vickers made no provision for cable runs or electrical distribution panels. Where exactly were the wires supposed to go? The dispute consumed weeks without resolution, but the equipment bay argument wasn't really about cubic feet. English Electric design was better for accessibility and weather protection during dispersed operations. Vickers' side-mounted access doors meant equipment would be exposed to weather during servicing. Worse, internal bay lighting would be visible for miles at night, hardly ideal for an aircraft hiding in forest clearings. Fuel location created another cause for disagreements. Vickers had drawn up a saddle tank positioned above the engines. The idea was to maximise the use of available fuselage volume. English Electric recoiled at the idea. Fuel in close proximity to the engine meant fire risk. The consequences of a fuel leak onto a hot engine didn't bear thinking about. Then there was STOL itself. The operational requirements specified short takeoff and landing performance for operations from damaged runways and dispersed sites. Vickers took this seriously, optimizing their design around it even at the cost of other performance margins. English Electric was skeptical. They continued to shy away from too much STOL work, reasoning that the aircraft would spend most of its life operating from normal airfields, never needing the capability. History would prove this point repeatedly, but in 1959, the argument generated friction rather than agreement. English Electric predicted, correctly as events would show, that allowing margins to tighten would only lead to problems later. Every technical disagreement reflected deeper institutional distrust. Neither company was wrong about their specific concerns, but neither could impose their solution on the other, and the ministry had no mechanism to adjudicate. Dividing the work. By March 1959, Vickers and English Electric had thrashed out a formal agreement on how they would work together. Vickers was nominated as prime contractor. The joint project team at Weybridge consisted of engineers from both companies, though somewhat English Electric heavy in practice, led by Henson. The initial division of effort split the aircraft into components. Vickers would handle the wings, front fuselage, including bomb bay, undercarriage and equipment. English Electric would take the remainder of the airframe, power plant and power supplies. This made bureaucratic sense. Each company would build roughly half the aircraft. Work would be shared 50-50, everyone could claim success. The problem was that neither company had agreed which design philosophy would prevail. After more meetings and more arguments, Vickers reluctantly conceded that the P-17's Delta wing was the one to go for. We'll cover the wing in detail in the following chapter. But if English Electric's wing was going to be used, it made little sense for Vickers to build it, and so was handed over to Wharton. The requirement changes. As if the design disagreements weren't enough, the target itself was moving. The fourth draft of GOR 339 had been issued in December 1958, but by February 1959 it was already being superseded. OR 343 emerged in March, and the changes were significant. As a result, the aircraft grew in size and weight. The low-level penetration height was redefined, 200 feet or lower, down from roughly 1,000 feet. This wasn't a minor adjustment. Flying at 200 feet demanded different structural margins, different systems integration, and different pilot workload. Speed at 40,000 feet increased from Mach 1.7 to Mach 2. The air staff described this as a cheap bonus. Thrust was promised to be made available anyway, so why not specify higher speed? The engineering implications of sustained Mach II flight, thermal management, material selection, structural fatigue were apparently secondary to political appeal. Electronic countermeasures capability was added. Ferry range increased from 2,000 to 2,500 nautical miles. The load classification number dropped from 40 to 20, meaning the aircraft now had to operate from firm grass surfaces rather than just concrete. A new mission profile also appeared that demanded a high-low-high profile with 100 nautical miles of supersonic cruise at altitude, followed by 200 nautical miles at low level at no less than Mach 0.9. It seemed that the performance inflation was to convince the Treasury that it was necessary to eclipse many existing types, the F-105, the A3 Vigilante, the Mirage 4, and even the Buccaneer to justify the program. Each enhancement looked reasonable in isolation. Together, they pushed the design towards the limits of what contemporary technology could achieve, and created an aircraft that had to be better than everything else flying just to survive the procurement process. The joint project team at Weybridge wasn't trying to refine an agreed upon configuration, they were chasing requirements that kept evolving and changing. The weight bomb. By April 1959, the first joint aircraft design emerged from the studies. It combined the P-17 wing with the Type 571's fuselage. However, English Electric had concerns. Freddie Page, heading the Walton design team, had established a rule of thumb. If the aircraft ever reached 75,000 pounds, it was time to rub it out and start again. The first joint design weighed in at an estimated 82,000 pounds fully loaded for a 1,000 nautical miles sortie. They were already 9% over Page's threshold, and this was before detailed design had even begun. The fuselage had been extended twice to rebalance after adding the P-17 wing, 5 feet to the rear plus 2¼ feet forward, then another foot at the nose and another 2½ feet at the rear. Each extension increased weight. Each increase required a larger undercarriage. The larger undercarriage needed bigger wheels needed deeper bays, and deeper bays reduced fuel capacity or increased fuselage cross-section, and on it went. The question which never got answered was which requirements could be relaxed to control weight. The ministry offered to relax the 3,000-foot takeoff requirement, but the companies declined, not for engineering reasons, but to maintain internal pressure. Plus, an admission that requirements couldn't be met would invite political questions about whether the entire specification was achievable. The spiral had begun, and the institutional machinery had no way to stop it. Vickers divided attention. While the joint team wrestled with configuration decisions, Vickers was fighting fires elsewhere. The company appeared flush with success. The Valiant had entered service as Britain's first operational V-bomber. The Viscount turboprop was selling internationally, but beneath the surface, trouble was brewing. Vickers had committed to 2 major civil programs, the Vanguard turboprop and the VC-10 jet airliner. Both were private ventures as required by the Ministry of Supply for civil development, and both were proven far more demanding than anticipated. The company had badly underestimated the development effort required. The Vanguard was consuming engineering resources. The VC-10 was worse, a technically ambitious 4-engine jet designed for hot and high operations from African to Asian airports. Its rear-mounted engine configuration and sophisticated wing created challenges that stretched Vickers' design capacity. The financial position was also deteriorating. The burden of 2 civil programs funded entirely by the company was unexpectedly heavy, and the VC-10 in particular demanded attention that might otherwise have gone to TSR-2. By August 1959, English Electric had had enough. Lord Caldecott, their chairman, approached the Ministry of Supply with a direct proposal. If Vickers was going to focus on civil aircraft and the potential merger with de Havilland being discussed, perhaps the TSR-2 contract should transfer to English Electric entirely. Let Vickers get on with what they wanted and let English Electric build the military aircraft they designed. The ministry refused. They'd forced this partnership into existence, and it wouldn't admit the arrangement wasn't working by allowing one partner to absorb the other's responsibility. The structure would remain as mandated regardless of whether it functioned effectively. The VC-10 would continue to drag Vickers' attention away from TSR-2 throughout the program's life. The November shock. By November 1959, Vickers and English Electric had produced production plans and cost estimates for submission to the Ministry of Supply. The documents landed like a bomb. The magnitude of the task was far greater than anyone had predicted. Cost estimates for getting the first aircraft to flight-ready condition had climbed from £35 million to £62 million, nearly double the original figure. English Electric estimated 44 months from intention to proceed to first flight. Vickers estimated 40 months. The lower figure was the one quoted to the ministry. Optimism, it seemed, remained the preferred currency in dealings with Whitehall. The ministry men who received these figures were shocked. But the institutional machinery had, again, no mechanism to ask whether the specification itself might be the problem. John Ragg, project engineer in charge of engine development for TSR2 at Bristol Siddeley, summarised the dysfunction years later. Put it simply, nobody had been in a position to say no to anything. The RAF couldn't accept reduced capability without questioning why TSR2 was needed. The Treasury couldn't provide unlimited funding without abandoning cost control. The industry couldn't admit which requirements were unrealistic without killing the program, and the ministry couldn't impose discipline without acknowledging OR 343 was overspecified. So the costs climbed, the weight grew, and everyone blamed everyone else. The trap closes. By the end of 1959, Henson's joint project team had achieved something remarkable despite the obstacles. They'd produced an agreed general arrangement, a datum aircraft that would evolve into TSR-2. But the achievement was fragile. Ivan Yates would later recall that just 6 weeks before the brochure was due, the aircraft design was neither stable nor did it meet the requirement. Only frantic last-minute wind tunnel work brought the design somewhere near what OR 343 demanded. The design seemed functional on paper, but not yet set in stone. The November 1959 brochure shock would be followed by more shocks as detailed design revealed new problems. The partnership was formed, the specification was set, now they had to design an aircraft that satisfied both, assuming, of course, that was still possible. By early 1960, the wind tunnel data sitting on Freddie Page's desk didn't quite add up. The wing that had looked promising in calculations was behaving badly with flaps down. Months of testing had consumed time the program didn't have, and the stability problems that should have been solved by now kept returning in different forms. The joint project team had tried enlarging the tailplane, adding ventral fins, shifting the center of gravity, each fix introducing new complications elsewhere. The breakthrough, when it came, required abandoning one of the design's original features entirely. The wing takes shape. The wings would become the TSR-2's most distinctive feature, that sharp delta silhouette recognizable in any photograph. But getting there required 18 months of wind tunnel frustration and a willingness to abandon ideas that seemed essential. The stability problems had become acute by June 1959. When the flaps came down to their full 50-degree position, the tailplane lost effectiveness, stalling at angles that should have been well within its operating range. The tailplane itself had grown through several enlargements, bringing it dangerously close to the size at which flutter could become a problem. Ground clearance during landing flare demanded further compromises. Engineers found themselves trapped. Every fix to one surface created new problems on another. The solution required sacrificing a feature they'd never thought of doing without. Look at any aircraft from the front and you'll notice the wings aren't perfectly horizontal. Most have some angle, either upward called dihedral or downward called anhedral. The TSR-2's original design used anhedral, that downward droop from root to tip, because it helped counteract the natural tendency of swept wings to roll when side-slipping. This was aerodynamically elegant. It was also causing havoc with the tailplane. The problem was interference. With the wing drooping downward and a tailplane mounted low in the fuselage, the two surfaces were too close together vertically. Airflow disturbed by the wing was hitting the tailplane and causing it to behave unpredictably. The most direct fix was to increase the vertical gap between them, and that meant eliminating the wing's anhedral entirely. By making the wing's underside completely flat with only a shallow angle remaining on the upper surface from the natural taper, the design team could separate the two surfaces enough to reduce the interference. The trade-off was significant. Without anhedral, the aircraft became susceptible to Dutch roll, that unpleasant coupled yaw-in and roll-in motion that would make even experienced pilots uncomfortable. But the stability gains justified the compromise. They would deal with the Dutch roll separately. To recover the lift lost in all these changes, the outer wing's leading edge gained a forward extension with a distinctive notch cut into it, creating a sawtooth pattern that was supposed to improve airflow at higher angles of attack. Combined with a 30-degree drooped extension along the wing's leading edge and the largest flap tailplane configuration yet tested, this produced the best results the tunnel had seen. But the sawtooth was about to become the design's biggest headache. Later testing revealed it caused pitch up, that dreaded tendency for the nose to rise uncontrollably at certain angles of attack, the phenomenon that had claimed the lives of many pilots in swept-winged aircraft since the early supersonic era. Worse, the sawtooth was shifting the aerodynamic center forward during transonic flight, meaning it was shifting the wing's lift balance point forward. Combined with the weight growth in the engines and the reheat system pushing the center of gravity forward, this created a balance crisis. The aircraft was becoming nose heavy at speed and tail heavy at rest. The sawtooth had been added to solve one problem and now was creating two more. And there was still the matter of Dutch roll. When they flattened the wing back in June, engineers had accepted increased susceptibility to that unpleasant urine and roll-in motion as a price of solving the tailplane interference. The assumption was the auto-stabilization system would handle it, but accepting the problem and ignoring it are different things. Someone at Wharton proposed addressing it directly. What if the wingtips themselves could provide the directional stability the flat wing had lost? The idea was counterintuitive. Rather than extending the wings outwards in a normal fashion, the outer portions would turn downward, angling towards the ground like drooping hands. Wind tunnel models were built and tested through November 1959. The concept worked on a simple principle. Those downward angled sections would act as small vertical surfaces at each wingtip, providing resistance to side slip that the wing's lost anhedral had previously supplied. By late 1960, the results were in, and they forced a decision. The downturned tip solved Dutch roll without creating new problems. Flap effectiveness barely changed despite the reduced span. The structural cost was the joint itself. Where the angled portion met the main wing structure, the engineering became more complex. But the lift losses proved negligible. The sawtooth, meanwhile, was failing at its original purpose while making everything else worse. Not everyone believed the wingtip data. In fact, heated arguments broke out over the wind tunnel analysis. The numbers looked too good. One engineer dismissed their report as thoroughly dishonest, strong language in any technical disagreement, but especially pointed when the program's future hung on getting the aerodynamics right. The debate dragged on, neither side willing to concede. Freddie Page cut through the noise. The sawtooth would go, the downturned tips would stay. And the lift that the sawtooth was supposed to provide? They'd get it in a different way, by extending the wing's trailing edge rearward, adding 24 inches of chord at the tip. This recovered lift without the pitch-up problems, without the balance complications, without the weight penalty. It was a package deal. Delete the feature that was failing, keep the feature that was working, solve the original problem through a completely different approach. A design freeze in late March 1960 locked in the changes, and the TSR-2 wing had finally taken on the shape that would become its defining feature. Blended solution. The design team's approach to the fuselage avoided a trade-off that other designers had simply accepted. There is an aerodynamic principle called the area rule, discovered by Richard Whitcomb, who was working for NACA in the early 1950s. The area rule, in simple terms, states that an aircraft's supersonic drag depends on how smoothly its total cross-sectional area changes along its length. Add a wing to a cylindrical fuselage and you get a sudden bulge in the area distribution and a massive drag penalty. The F-102 proved the point. Convair's Delta Interceptor was supposed to be supersonic. The prototype couldn't break Mach 1. It topped out at Mach 0.98, an embarrassment for an aircraft supposed to chase Soviet bombers. Only after they pinched the fuselage into a wasp-waisted shape, the famous Coke bottle look, did the aircraft finally go supersonic. But that solution cost internal volume exactly where fuel tanks and weapon bays needed to go. The TSR-2 design got around this issue by stretching the wing roots deep into the fuselage itself, blending the two into a single aerodynamic shape. The cross-sectional area changed smoothly along the aircraft's length, which met the area rule's requirements without the Coke bottle pinch. Now 80% of the fuel went into the fuselage itself. Forward tanks stretched from the equipment bay back to the air intakes, rear tanks wrapped around the engine tunnels, and wings carried the rest. Total tankage reached around 5,500 gallons, which would give the aircraft the combat radius that OR 343 had specified. Controlling the beast, the flying surfaces abandoned convention entirely. An all-moving tailplane mounted low on the rear fuselage handled both pitch and roll. The two halves could move together for climbing and diving, or differentially for banking, tailerons the engineers called them. There were no ailerons on the wing itself, the tailplane did everything. The fin was all moving too, so no conventional rudder, the entire surface pivoted. This gave the aircraft authority across a huge flight envelope, from 200-foot terrain following to Mach 2 at altitude, but it also meant the aircraft was inherently unstable in certain flight regimes. Without electronic assistance, pilots would have struggled to keep it pointing where they wanted. The auto-stabilization system was supposed to handle this, which we'll cover in detail in part 2 of this series. But in essence, the gyros would sense unwanted motion, computers commanded corrections, and the control services responded before pilots even noticed the problem. Whether the system would have worked as intended remained open to question. What lay ahead? The Vickers and English Electric teams had drawn up an extraordinary piece of engineering by any measure. The wing worked. The control services provided authority across the flight envelope running from 200 feet to above 50,000, and that blended fuselage held together aerodynamically without the compromises other designers had simply accepted. But an airframe is still a shell until you fill it. The navigation system that would guide this aircraft to its target at extreme low level in darkness and bad weather? Well, that just existed mostly as specifications and supplier contracts. Terrain following radar, the single system that justified the entire low-level concept, was absorbing 40% of the electronic development budget and still hadn't flown. Nobody in British aviation had attempted to integrate 14 major avionics systems into a coherent whole at this scale, and the computers being built were only the beginning of that challenge. Bristol Siddeley's Olympus engines that were supposed to deliver 30,000 pounds of thrust in reheat, instead they were delivering compressor blade failures, combustion instabilities, and a development cost trajectory that had already alarmed the Treasury. And the weight would start to climb. Every system that went from specification to hardware came in heavier than predicted. Fixes added structure. More structure demanded more fuel to maintain range, which demanded yet more structure to carry that fuel, which still added more weight. Once started, the spiral had a momentum of its own. What the engineers could see on their drawing boards was perhaps the most sophisticated combat aircraft any country had yet designed. How Britain's industrial and political system would actually deliver it? Well, that's a question part 2 will answer. Right, so that's part 1. I've been living with this aircraft for months now, and the thing that makes her story fascinating to me is just how much went into her before she ever left the ground, and we haven't even got to the really dramatic stuff yet. Part 2 is where it really gets interesting, where we get into the engines, electronics, the avionics, terrain following radar, the computers, the systems integration that was supposed to make this beautiful machine actually work as a weapons system. The engines, the weight spiral, all that stuff. And of course the first flight, and then the politics that killed her. Dennis Healy, the Treasury, the Americans, the F-111, the whole sorry business. That's coming soon. So if you haven't already, please subscribe, hit the bell so you don't miss it. But I wanted to say something about why this one matters to me. I was at Cosford not long ago, standing in front of XR220, and people were walking past her without a second glance, which is fine, it's a museum, there's a lot to see. But this aircraft, this thing that people just stroll past on the way to the gift shop, it represents one of the most ambitious engineering projects this country had ever attempted. Thousands of people worked on her. Careers were built and destroyed around her. Political fortunes rose and fell. And all that history, all that ambition, all those arguments, it's all invisible unless somebody tells her story. That's why I like to do these deep dives. The aircraft are interesting. Obviously they are. But the stories behind them are extraordinary. The politics, the engineering, the personalities, the impossible decisions. TSR2 has undoubtedly cast a long shadow over the British psyche. 60 years on, people still argue about whether cancelling her was the right call. Tells you something about how deep this one goes. Anyway, thank you for watching. Genuinely, these long form videos take a huge amount of work, and the fact that you've stuck with me for almost 80 minutes means the world. Also, if you want to help out for the next TSR2 video, please feel free to drop me an email. My email is in the description, and I'd love for you guys to have a hand in the next one. So if you've got any like stories, photos, videos of TSR2 that you want me to include in the next video, please let me know. Drop me an email. More than happy to see what we can do. Anyway, so if you've enjoyed it, please leave a comment. Let me know what you think, and I'll see you in part 2. Toodaloo.